cleared out any issues related to accommodation and stuff. Is everything okay? Or if you have issues, please get back to us. We'll be happy to help you. And briefly, let me say what you expect in next 2 weeks. There will be essentially 8 modules on various topics. 3 of them would be on stochastic PDEs, and 5 of them would be on deterministic PDEs. And each module will consist of, I think, 3 to 5 lectures. So you get ample time to understand. And yeah, and please feel free to ask speakers questions. So all of them are here. You can ask anytime questions. So that will help you. Okay, and so today our first speaker is Professor Hyunju Kwon. So she defended her PhD at UBC, University of British Columbia in Canada in 2019. And then she went to IIS at Princeton for a postdoc. And in fact, she worked with Camilo for a few years. And eventually she joined ETH as an assistant professor. So yeah, so it's a great pleasure to introduce her.
I'd like to thank to the organizers for having me this beautiful place. And in this lecture series, as you see from the title, Vikram and I will introduce so-called Wavelet-inspired Nash iteration, which we developed in our recent resolution of L3-based strong-on-Sagar conjecture, jointly with Matt Novak. So the reference will be our recent paper. Okay, so to motivate you, let me start from the strong-on-Sagar conjecture. Can everyone see this board? Okay. So you may heard about on-Sagar conjecture and also strong on-Sagar conjecture. Both conjectures are on the 3D incompressible Euler equation. So let me first introduce the equation. So these equations describe the behavior of incompressible fluid. You can imagine water. And for our purpose of the talk, let me restrict our domain to the periodic cube. So you simply imagine some periodic cube. I just draw the two-dimensional picture, and then some water flow inside. Then to describe the behavior, all you need is the velocity vector field. So this is time and space. So this is the periodic box, and it's given as a vector field. And then pressure, which is defined on the same domain, but it's a scalar function. Okay. So velocity and pressure. So with this, so taking these two as an unknown, one can introduce the Euler equation given as follows. Okay. The first equation is called momentum equation, and it can be simply explained by Newton's second law of motion, which is F equals ma. So this first two, the left-hand side term describes the acceleration of a fluid particle. And yeah, so for example, if you look at this, obviously we should have the time derivative of the velocity. And since the fluid particle moves in time, that generates this term. And then this acceleration will balance with the force acting on a particle. And Euler assumed that there's no effect of friction, so the only force is generated by pressure. And since water flows from the area of high pressure to the area of low pressure, you can imagine that this would be the right direction. Okay? On the other hand, the divergence-free condition explains the incompressibility. So unlike the air, which is compressible, water is incompressible. And mathematically, it means that the density remains unchanged along the flow. And now if you combine this with the mass conservation, you can see that divergence. Okay. All right, so this is Euler equation. And now let's take a smooth solution to this equation, and let me talk about energy conservation. So here, what I mean by smooth solution is that the solution which is differentiable in space. And now if you take the inner product, the first equation with velocity, just simply by product rule, one can obtain the following equation. And if you use the divergence-free condition, the second term can be written as a divergence force. So this one can be written as well. And now you take integral over the entire domain. So in our case, it's the periodic domain. Then you have the following. And then the second term will vanish because of the periodic boundary. So what does this equation mean? Well, physically, so the following quantity, this 1/2 of the square integral of the velocity corresponds to the total kinetic energy. And here what I mean by total is we sum all the kinetic energy over the entire domain. And this equation tells us that this total kinetic energy conserved in time. Right? So, okay. And if you look at the first equation, this equation also has a physical meaning. If you take now integral over some arbitrary region omega, then this is what you can see. And there will be, so if you use the divergence theorem, actually you will have some integral over the boundary, and it's equal to 0. So this equation describes the change of the kinetic energy over the region omega, and it tells us that the change of kinetic energy balanced with the change through the boundary. So this means that there's no creation or dissipation of kinetic energy. So this tells us that the kinetic energy is conserved even locally in space. Which is called local energy equality. If you have any question, feel free to interrupt. Okay, but in this computation, as I assume that the solution is smooth. And now you can raise the following question. Do this conservation of total kinetic energy and local kinetic energy persist even though we lower the regularity of the solution? And if not, what will be the critical space? So to give an answer to this question, one can first simply apply the mollification technique. Okay. So does everyone know mollification? Okay. So first let me denote the mollifier as law epsilon, which is given as 1 over epsilon cubic, and let's say x over epsilon. And here law will be some compactly supported smooth function which has the unit mass. And then the mollified velocity will be then given as follows: the convolution between the mollifier and the original velocity. And the purpose of this mollification is the following: even though the velocity has low regularity, through this convolution, you can get a smooth object. So so mollification in some sense is an averaging operator. So you can consider so that the U epsilon is the mollified one is smooth. Okay. And since we know how to prove the conservation for smooth solution, what we're gonna do is the following: we take the mollification to the equation, and we write the equation in terms of the mollified velocity, and then repeat the same computation. So if you apply this mollification, then what you have is the following. Well, first, since the derivative commute with the mollification, this is what you have. But in the nonlinear term, since the multiplication doesn't commute with the mollification, here you will have the following term, and this produces the error. So these two are same. And when you take the mollification, what you actually get is this. Okay. And now if you repeat the same computation, what you get is the following. On the left-hand side, again, you will get the time derivative of the total kinetic energy of the mollified velocity. But we have some term on the right-hand side, okay, which can be written as follows. The integration is over the entire. Okay. And now we take the integral over time from 0 to t. And on the left-hand side, what we have is the following. The difference between kinetic energy between at time t and time 0, and on the right-hand side, we have this. And now we assume that our velocity is continuous in time and, let's say, L2 in space. And now if you send epsilon to 0, you can see that the first term, so the left-hand side term converges to the following terms. And what we want to show is this quantity is equal to 0. So the question boils down to the following. When we send epsilon to 0, whether the right-hand side quantity converges to 0. Okay, here, let me use the component-wise expression. So the question is whether the right-hand side quantity is equal to 0. Okay, so to show this, let me first give you some remarks on the following commutator. Okay, so the bracket is maybe. So this commutator looks like this. We have some multiplication of two functions, and we apply the modifier minus the modified f times modified g. And now you can expand, this expression in the following way. The first term looks like this, f x minus y, g x minus y, and with the modifier y. And then the second term looks like f x minus y, and say g x minus z, and then we have modifier. And here, if you use Poisson summation formula, the integral is actually taken over the entire domain. Okay. And here, since the mass of the modifier is 1, so you can simply put the following integral. Okay, so now if you combine these two, we have the following. And you can notice that this quantity remains the same even after you swap the variable x and z. Okay, so this will be, okay, let me just write. Minus and then again this quantity will be same with the average of these two. So you will have And since it's average, 1/2. Okay, so now my claim is the following. If the solution velocity has the following Bezoff regularity, for alpha greater than 1/3, then the right-hand side term, so this one, will be indeed 0. And, okay, so what is this Bezoff norm? The Bezoff norm is defined in the following way. So we take L3 norm of U and then consider the velocity increment under L3 norm, and this will be bounded by y to the power alpha when y is not 0. So simply speaking, you can consider this Bezoff space as an L3 analog of the Holder space. Okay, so to see this now, let me use our remark. If you use remark, the right-hand side term can be written as follows. So there's integral between 0 and 2, and over the torus. Then we have also integral in y and z variable. Okay. And then you epsilon I, no, not epsilon, x minus y, I, x minus c, times and then we have partial I u epsilon g dx dy dz and the s 1/2 maybe minus. Okay. And now we apply the L3 norm in space-time. So Holder inequality. So we take the L3 norm in space-time to this and this and this. And this will be bounded by L3 norm of the velocity increment and squared, because there are 2. And then times the modifier and we have L3 norm of the derivative. Okay. And now you apply the Bezoff regularity, then this will be controlled by z, y minus t to the power 2 alpha. And now you apply a change of variable. here, then you can show that this will be epsilon to the power 2 alpha times the Bezoff norm of U squared. And then we have this term. And for this term, by doing somewhat similar computation, you can also show that it is bounded by alpha minus 1 and times the Bezoff norm. This I will leave it as an exercise. And once you have this, you can easily see that this quantity converts to 0 when alpha is greater than, as epsilon goes to 0 when alpha is greater than 1. So the claim holds. So to summarize, we can obtain the following theorem for any weak solutions to the Euler equation, which has the following regularity: continuous in time and L2 in space, and L3 in time and Bezoff regularity for alpha greater than 1/3. The total kinetic energy conservation. In the sense that, in the following sense, the kinetic energy of U in time t, at time t, is same with the initial kinetic energy. Any questions?
How do you bound that gradient term?
Uh-huh.
How do you bound the gradient term?
So I leave it as an exercise. So this one will be bounded by epsilon to the power alpha minus 1 and this Bezoff norm. And again, you write this modification as the convolution form, and then you work a bit.
So what you do if you have a bounded domain?
Bounded domain.
Is the result true? What you
You mean total kinetic energy conservation is
Yeah.
true? Well,
play this trick here.
okay. Well, it depends on boundary condition, right? It should.
Yeah.
Because the divergence term should vanish.
But it's true. The result.
Yeah, if you have, for example, the Dirichlet boundary condition, it should be true. Any other question? Okay, now I think I need to erase this board. I forgot to say that this theorem was obtained by Constantine, E and TT. I think it was 1993, based on Einstein. Okay, so far I've talked about the total kinetic energy conservation. And now let's talk about the local kinetic energy conservation. So if you work a bit more, one can obtain the following theorem, which was first introduced by Duchamp and Lobert, 2000, which says the following: for any weak solution to the Euler equation, if it's S3 integrable in space-time, then it satisfies. Okay, maybe I will just write it. Maybe satisfies the following equation. In distribution sense. And where the distribution can be written as follows. Okay, so from the proof of the total kinetic energy conservation, you've already seen the square of the velocity increment. And if you work a bit more, you can even show, okay, there's derivative. You can even show another, the cubic velocity increment. For the proof, I will refer to the paper of Duchamp and Lobert. But so the point that I want to mention is the following. Once you have this as a corollary, you can easily show the following. So again, for any weak solution, which is S3 integrable in space-time, the local energy equality holds. Sorry, what I want to say is the following. If it has a Bezoff regularity for alpha greater than 1/3, then the local energy equality holds. In other words, the distribution on the right-hand side will vanish. And this is easy to see because you have a cubic of the velocity increment together with the Bezoff regularity. This will be controlled by y to the power 3 alpha. And again, if you use simply change of variable, you can see that y alpha greater than 1/3 is the critical. Any question? Okay, so once you have this, our question boils down to the following. So So now we have a total kinetic energy conservation and local kinetic energy conservation as long as we have the following regularity. So now question is the following space, so B1 third 3 infinity, the critical space for these conservations? This question sounds purely mathematical, but in fact, the answer to this question is closely linked to the theory of turbulence. So from now on, I'm gonna talk a bit about some fundamental features in turbulence theory. And along the way, I will also talk about the Onsager's. Okay. I lost numbering. Let's say 3. Well, okay, it's proved. So let's see, Onsager's. So let me first introduce the Navier-Stokes equation. Okay. So as mentioned earlier, the Euler equation is ignore the effect of friction. But in the real world, friction is always there. So by incorporating such effect of friction, the Navier and Stokes equation was introduced. Which is given as well. Okay. And obviously, this extra term describes the effect of friction. And here, RE, or RE, you can just simply consider it as some positive number, which is called Reynolds number. You will see the role of Reynolds number in a minute. Okay, so with this equation, of course, our ultimate goal is the following. You give the current information of the fluid, and you want to see how it behaves at any future time. But to answer this question, one of the main difficulty comes from so-called turbulence. So here, what I mean by turbulence is that the chaotic behavior of fluid. Okay? So to understand the behavior of the solution, we are very interested in the turbulent flows. And for that, we are also particularly interested in the behavior of the solution to the Navier-Stokes equation as the Reynolds number goes to infinity, because when Reynolds number goes to infinity, the flows tends to be turbulent. Okay. And in this context, the Euler equation, you can consider it as the extreme case when Reynolds number is equal to infinity. Okay, so now let me introduce the most fundamental features of these turbulent flows, which is called anomalous dissipation. Okay, so since the turbulent flows are so chaotic that we can't talk about the behavior of each single flow, but when you take some average, there are some common properties, and this is one of them. And it can be formulated in the following way. When you take the, let's say, long time average of the dissipation rate of total kinetic energy, So this bracket means a long time average, and send the Reynolds numbers to infinity. Then this number does not converge to 0, rather it converges to some positive number. And this is somewhat strange because we know that for smooth solution to the Euler equation, that it has a 0 dissipation rate of total kinetic energy. Indeed, if you consider the smooth solution to the Navier-Stokes equation, the term inside is same with the following. And of course, this term is again generated by this, the dissipation term. But this formulation tells us that even though you turn off the effect of friction by sending the Reynolds number to infinity, the energy continues to be dissipated. So this phenomena is quite strange. So it is called anomalous dissipation. And around 1960s, many physicists tried to understand the mechanism behind this property. Okay, and what they said the following. So imagine that the turbulent flows consist of the different size of eddy, the circular motions. Then what's happening in turbulent flows is the following. These large eddies are break into the smaller size of eddies. And this process is continued until it reaches the scale where the friction is significant. Okay. And then what happens if we increase the Reynolds number? Well, then the factor in front will be smaller, so you can actually continue this process longer, and it will generate even smaller size of eddies. Okay. And then, okay, so since the Reynolds number is large, this factor will be smaller, but since you have a more derivative cost from u, so these two will balance, so that's how you can keep the positive balance in the limit. So this phenomena is called the energy cascade. And Onsager said that since this process occurs without the assistance of a friction, even Euler flow can have total kinetic energy dissipation. Okay, and he even suggests what will be the critical space for the total kinetic energy conservation, which was known as Onsager's conjecture in mass community, and now with the proof, we call it as Onsager theorem. So let me state this theorem. The theorem consists of two parts, the conservation part and non-conservation part. The conservation part says that for any weak solutions in continuous in time and C alpha in space for alpha greater than 1/3 satisfies the total kinetic energy conservation. And the non-conservation part says that for each alpha less than 1/3, one can always find a weak solution to the Euler equation in the following space, in the Holder space, such that the total kinetic energy dissipation. The conservation part is a simple corollary of the Constantine ETT's result, while the non-conservation parts was proved relatively recently. Well, first of all, Phil Eset constructed a solution whose total kinetic energy is not conserved. I think it was 16. But in the real world, the creation of total kinetic energy is not allowed. So by refining Eset's proof, Buckmaster and Drelis Cyclohidi and Vladiko, I guess 17, proves the dissipation of torque. Any question? Okay. Okay, then what happened at the critical space? So this results tells us that the continuous in time and C1/3 in space is the critical space for the total kinetic energy conservation. And well, what happened in the critical space still remain as an open problem. So in this critical space, we don't know whether total kinetic energy is always conserved or not. But in fact, if you also combine this Onsager theorem with the Constantine ETT's result, you can also see that the following Bezoff space is the critical space for the total kinetic energy conservation, because the function in C alpha space is always in the Bezoff space. Okay, so now you may ask the following question. So what is the right space for the turbulent? And this motivates, okay, so this question is related to the second fundamental features of a turbulence, which is called intermittence. So what's the difference between the Holder space norm and Bezoff space norm? The difference is under which norm are we going to measure the velocity increment, right? So the intermittency tells us the following. If you measure the velocity increment in LP norm and take some average, let's say long time average, and then send the Reynolds number to infinity, then this quantity exhibits very nice power law as long as y is, okay, this displacement is in the inertial range. Meaning that the range where the energy cascade happens. The reason where you can ignore the effect of the external force and the dissipation. Okay. Yes? So the range, so roughly speaking, the range where this energy cascade happens, so the range that you can ignore the effect of the external force and the dissipation. So it's a sort of purely turbulence region. Any other question? So you, when you measure these kind of things, you usually measure experimentally, and then so you just measure this quantity over time. And at some point it will stabilize to something, and then you take that as a long time average, because you expect that that quantity will continue. Then for a long time that will be the average. Okay, if there's no more question, let me continue. So this suggests the following: if you take 1 over p's power on both sides of on this power law, then this suggests that the right space for the turbulent flows would be the following Bejob space: B SP, P infinity, for SP. The differentiability parameter is given as zeta P over P. Okay, now then question is, what should be this differentiability parameter SP or zeta P? This has a bit of history. So initially, under the assumption of the self-similarity, Kolmogorov expect that this zeta P will given as 1/3 times P. So in other words, SP will remain as 1/3 for any P. Okay. So this is the Kolmogorov's guess. But in practice, the numerical experiments actually shows a deviation. So what you actually obtain is some following type of curve. And here, at the intersection is P is equal to 3, and zeta P is equal to 1. So more precisely, what we can tell from the experimental result is the following. The turbulent flows are in the space B 1/3, 3 infinity. And if P is less than 3, then the differentiability parameter stay above 1/3, while P is greater than 3, then this parameter stay less than 1/3. But we don't have the agreed value for SP when P is not equal. Okay, so to summarize, in a broad sense, the intermittency refers to a deviation from the Kolmogorov's guess. And then, so when you say the flow is intermittent, we expect that when you measure this flow with different LP norm, it has a different differentiability parameter for different P. And in particular, when you measure in L3 norm, the differentiability parameter is 1. Okay. So after Onsager's theorem was obtained, people tried to incorporate this the feature of intermittency, and that motivates to consider the intermittent Onsager's theorem. Which is obtained by Nova and Biko in 22. So they construct that. There exists a weak solution to the Euler equation in the following space. Such that, again, the total kinetic energy dissipates. So compared to the Onsager theorem, constructing weak solution whose total kinetic energy dissipate is the same, but the solution space has been replaced. So instead of Holder space, the constructed solutions are belong to the following space. And in particular, if you use interpolation, you can see that when you measure the velocity with different LP norm, the differentiability parameter indeed changes. And in particular, when this space is actually included in the almost critical space for the job space. And lastly, when you measure the velocity with L2 based norm, the differentiability parameter indeed goes above 1/3. So the constructed solution really reflects the intermittent nature of it. And one remark is that this theorem was proved based on their previous joint work with Buckmaster and Masson. Okay, any question? If not, let's move on to so far we've talked about the conservation or non-conservation of total kinetic energy, and now let's talk about the local energy side. Okay, so strong on Sagar's conjecture. And of course, local energy conservation is stronger statement than the total kinetic energy conservation. If one can construct the solution which breaks the total kinetic energy conservation, it automatically breaks the local kinetic energy conservation. But that's somewhat meaningless statements, and we want to reflect the behavior, the local behavior of the solution. So let me first talk about the following theorem, which is obtained by Duchon and Robert again, and stated in the following way. What was it? If an Euler flow can be realized as a limit, as the limit of suitable weak solutions to the Navier-Stokes equations, in the following sense. When you send Reynolds number to infinity, it converts to the Euler flow in L3 topology. Let me write it here. Then such Euler flow should satisfy the local energy inequality. Given as follows. In distribution. So what does this theorem tell us? Well, as we've discussed, the real world fluid flows are, described by the solution to the Navier-Stokes equation. So when you talk about the physically meaningful Euler flow, you expect that such flow can be realized as a limit of physically meaningful solution to the Navier-Stokes. And this theorem tells us that if that's the case, such Euler flow should satisfy the following local energy inequality. So one can use this local energy inequality as an admissible condition for this physically meaningful solution. Okay. And when it comes to this inequality, well, its physical interpretation is the following. We already know the equality implies a local kinetic energy conservation, and this strict inequality allows the extra dissipation of kinetic. So it prevents the creation of kinetic energy locally. And now let me introduce strong side. Well, first in C0 frame. So initially, following the Onsager's convention, we consider the conjecture in again on Holder space. And so the conjecture has again two parts, the conservation part and non-conservation part, where the conservation part says that, again, any weak solution to the Euler equation in continuous in time, C alpha in space for alpha greater than 1/3 satisfies the local energy equality, the local kinetic energy conservation. Let me just write. Yes. Sorry? Sorry. So far I wrote any weak solution in Holder space for alpha greater than 1/3 satisfy the local kinetic energy conservation. I will write bigger. Okay, and the non-conservation part says that for alpha less than 1/3, one can find a weak solution in the, again, Holder space such that it satisfies the local energy inequality but not the equality. Not the local energy equality. And this is equivalent to the following. It satisfies, again, the local energy inequality and satisfy the total kinetic energy dissipation. Well, the reason is the following. Solution satisfy local energy inequality means that locally conservation or dissipation occurs. But if it doesn't satisfy equality, then in some region, the dissipation should occur. Then it will have total kinetic energy dissipation. And you can also think that conversely, let's see. In distribution sense.
You can upgrade the time regularity.
You mean?
C alpha in space time.
I mean, based on construction, yes. 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 Okay. So the conservation is again the simple corollary of the Duchon and Robert's results. but the non-conservation part still remain as an open problem. And there are only few partial results known. So the one is that by Drellis and Cyclohiri, in, I think, 2010, they constructed the desired solution in L-infinity space. And then, I think Iset constructed whole continuous solution, I guess 17, for alpha greater than, alpha less than 1/15. And then this range of the exponent has been extended by Drellis and myself up to 1/7. I think this is 21. Okay, I'm not sure, 20. Okay, so there's a gap between 1/7 and 1/3. And as you shall see, so I will show it probably in the next lecture, if you do the heuristic computation, it tells us that the standard Nash iteration actually give a limitation of this range of alpha, so it goes only up to 1/4 rather than 1/3. So there's a gap between 1/7 and 1/4, which probably requires the development of several technical tools. And then to fill the gap between 1/4 and 1/3, you probably need a new idea. So that'll be the challenge. Okay. It's also, we don't know. I think it requires some development of technical tools. I mean, at the level of heuristic, it's supposed to work, but there's no result. Okay, so as we discussed before in the total kinetic energy side, now one can ask, can we incorporate the intermittency? So that motivates us to consider the strong Onsaga conjecture in L3 based, L3 based, let's say, L3 based strong Onsaga. Okay, well, okay, since it's proved, let me call it as here. And this theorem was obtained by Vikram here and myself together with Novak, 23. And we constructed the following solution. So weak solution to the Euler equation in the following space, continuous in time, and b 1/3 minus 3 infinity intersect with L infinity minus, such that, again, the local energy inequality holds, but not the equality, so the total kinetic energy is
Why do you need it to be all LP less than technical?
well, so to say this is intermittent, you wanted to show that this, when you measure the solution with different LP norm, the differentiability parameter really varies. And through this interpolation, you can see. So without this, we can't say anything about. Okay, so the constructed solution reflects the total kinetic energy dissipation and the intermittency, which are the fundamental features of turbulence. ideal turbulence. And then it also satisfies the admissibility condition, the local energy. Okay, and as mentioned earlier, the proof will be based on what we call the wavelet-inspired Nash. How much time do we have?
10, 15 minutes.
Okay. So now, before we go into the wavelet-inspired Nash's iteration, let me first talk about Nash's iteration. Well, broadly, it is also called convex integral. Okay, so Nash's iteration was first introduced by John Nash in his construction of the counterintuitive example of C1 isometric embedding, but I believe that this will be covered by Camillo. So here, let me just describe the Nash's iteration in an abstract way. So the Nash's iteration how should I say, generates a sequence of approximate solutions by successively adding high frequency corrections to the initial approximate solution. And then as their limit, we obtain the desired solution. So Nash's iteration is some way to construct the wild solution. And then the way to do is the following. So by using induction argument, so the iteration is essentially based on induction argument. We're gonna generate a sequence of approximate solution, and we're gonna do this by successively adding high frequency correction. And this will be clearer if you see how the application works for the Euler equation. So first, we should talk about what is our definition of approximate solution. So the inductive hypothesis is given as follows. So at Q step, we have the following approximate solution, which is given as a solution to the Euler-Reynolds system. So compared to the original equation, we have extra error, which is divergent form. The error So this error is called stress error. And we want this error to be symmetric because matrix which satisfies that when you apply the C0 norm, so this is the C0 norm in space-time, converges to 0 as Q goes to. And this way, you can show that the limit solution will satisfy the Euler equation in distributions. And now let me explain how to introduce this system for the approximate solution. So one way is the following. Assume that we can successfully learn the Nash's iteration. Then our eventual solution will be, let's say it's constructed in the following way. So this is the frequency line. And let's say the initial approximate solution, denoted by U0, has the frequency lambda 0. And then, if you follow the Nash's iteration at the next step, we're gonna add a correction that's denoted by W1, whose frequency is much larger than the one in U0, let's say denoted by lambda 1. And this will form the summation between these two will be our next step approximation. And then we just repeat this process. So you add another high frequency correction and form U2 and so on. So then our eventual solution will consist of this increasingly higher frequency building blocks, right? And from this perspective, you can consider the Q-step approximate solution as the one, so the solution with the frequency projection operator applies to the ball of radius lambda q. Does it make sense? Okay. Then the natural equation for this approximate solution would be the equation for this this projected one. So what one can do is you simply put the solution into two parts. The one is the average part, which corresponds to this projected one, and plus some extra perturbation. Or you can also consider it as a noise, and assume that there's a frequency gap between these two. And then you write the equation for this averaged one, the projected one. Then you will get the following. And in fact, on the right-hand side, what you're gonna get is divergence of minus W tensor W, and it's average, so projected on, let's say, lambda q, if you're working on this. So it's quite natural to expect that this error is a symmetric matrix. And as you will see later, indeed, this RQ will be corrected by the low frequency of the perturbation. Okay, so now let me talk about how to run this inductive argument. Well, since this system is underdetermined, you can construct the initial approximate solution rather easy. You can even add some property that you want. So the main question is, for given Q-step approximate solution, how to construct the next step approximate solution so that the new error is much smaller than the previous step. So the goal is, for given Q-step approximate solution, how can we find the goal? So like we want to find the new perturbation defined as follows, such that the new error is much smaller than the previous step error. And to achieve this, one can first introduce the equation for the perturbation. So for simplicity, let me just write WQ plus 1 as just W. Then the equation for the perturbation is the following. Okay, I missed this term. Okay, and now what do we know about the new correction? The only information that we have is this will have much larger frequency than the previous step solution, say UQ or RQ. So it's quite natural to decompose this equation based on the frequency. So let's consider the low frequency part. Equation, and there will be also high frequency. Okay. Well, so first, if you look at these three terms, this will have high frequency because, well, the derivative wouldn't change the frequency, and in the interaction of low-high frequency, we only have high frequency. Does it make sense? So these three terms all goes to the high frequency part. And then this nonlinear term will generate both low frequency and high frequency. So here we have the low frequency part, W tensor W, and then high frequency part. And obviously the RQ will be in this low frequency. And well, we'll choose the perturbation of pressure so that this quantity is zero. So let's ignore the pressure. And now recall our goal. We want to make the new error much smaller than the previous step error. And for this, you really need to cancel out the previous step error. The term who can do that job is the low frequency part of the tensor product between the new correction. So the strategy is that you're going to find a new correction in a way to solve the low frequency part equation. And then you put all the remaining error into the new error. Okay. And then you can ask, so how can we guarantee the smallness of the new error? Okay. But here the observation is the following. All the left-hand side term has high frequency. More precisely, their frequency will be essentially same with the frequency of W, which is lambda Q plus 1. So when you invert the divergence, you can think as taking inverse of the derivative cost, then you will gain a factor 1 over lambda q plus 1. And now if you choose this lambda q plus 1 sufficiently large, you can make the new errors. So that's the sort of the idea behind. And now if you describe what's happening here in the picture, it can be given as follows. So in the frequency space, let's say the RQ has a frequency localization at lambda q. Then from the low frequency of this nonlinear term, so we design the perturbation so that it solves the equation. So that way we're going to cancel out this error. And then the remaining error will generate a new error at the frequency W, lambda q plus 1, with a smaller size. And then you can just keep iterating. So this is how Nash's iteration works for the Euler equation. This time's almost up. Okay. And so here I didn't explain how to achieve the Holder regularity of the solution, which requires the which requires us to quantify the size of error. So next time I will show how to do error estimate in the heuristic sense, and then there you will see how to achieve Holder. Okay. Is there any question? If not, let me stop here.
Okay, so thank you. Any questions or comments? Yeah. So online, I don't know, can they hear? So any questions from online? So any questions?